Is it a go? Thank you. All right. Welcome, everybody, to our last seminar of the semester. It's a great pleasure to have here Dr. Wright, John Wright from Columbia University. Dr. Wright is an assistant professor in ECE, or EE, I guess it's not ECE, EE at Columbia University. He received his PhD from the University of Illinois, Urbana-Champaign, in 2009. He then subsequently went to work for Microsoft in Beijing from 2009 to 2011. His research interests lie in the area of high-dimensional data analysis, and recently he's been working on methodologies for robustly recovering structured signal representations from incomplete and noisy corrupted observations, with, of course, emphasis on vision and imaging. He's received a number of honors and awards, including the Lemelson Illinois Prize for Innovation for his work on face recognition, and 2008-2010 Microsoft Research Fellowship, and he also got the Best Paper Award at COLT. COLT is the Conference for Learning Theory, on Learning Theory in 2012, and he also got the 2015 PAMI T.C. Young Research Award and the recent 2015 Sparse Best Paper Award with his students. And it's a pleasure to have him here talk about some dictionary learning methodologies. And thank you for coming, and the floor is yours.
Okay, wonderful. I'm going to talk a little bit about dictionary learning today. I'm going to talk about theory, algorithms, and applications, but this is going to be largely a theory talk. So we'll start out talking about some work that we've been trying to develop methods for learning dictionaries for sparse representation that come with provable guarantees. And so we'll see that that leads us to some kind of interesting phenomena in high-dimensional non-convex optimization, a few things that have some generality to it, and then we'll close by looking at some applications. So, as I said, this is largely a theory talk, but still I'd like to start with an experiment, because actually the work that I'm going to tell you about sort of grew out of this experiment. So, dictionary learning, surveying the audience, I think that most of you have heard about this. So the goal in dictionary learning is to form a concise approximation for a given signal or class of signals. Right? So I have some data to represent it. So here, what I'm going to do is I'm going to follow very standard practice in image processing and in some areas of machine learning. So I'm going to try to take this natural image, this fish here, and I'm going to try to learn a concise approximation for patches of this image. Okay, so what I and what people in this area do is they take this image, chunk it up into little patches. So these might be 4 by 4, 8 by 8, 16 by 16, convert it to a bunch of little patches, stack these things up as columns of a big matrix, and then I'm going to look for a factorization of that matrix. Okay, so if my patches have n pixels in them, and I have p patches, then my matrix Y here is of size n by p. Okay, so that's my data matrix, and what I'm going to do is to try to concisely represent it as a product of two matrices. So I'm going to try to write Y as Q times X. Here, Q is the dictionary. Okay, so the columns of Q are some sort of basis that I'm going to use to represent my signal. And X is a matrix of coefficients. And since I would like my representation to be as concise as possible, both for compression, also potentially for other tasks, to regularize the image so that I can do recovery, denoising, etc. I would like to make the representation sparse. So what I'm going to try to do is I'm going to try to write Y as Q times X. Q is the dictionary, X are the coefficients, and we're going to try to make them as sparse as possible. Okay. Now, there's a detail that always comes up, which is where my dictionary should live. And in this experiment that I'm going to show you, I'm going to constrain my dictionary to live on the orthogonal group. Whether this is a good idea or not is very much problem dependent. Generally speaking, if you're trying to learn from a a more concise or compact, sort of a smaller set of images than a smaller dictionary is a good idea. Here we're learning from just a single image, so we'll be okay with a square dictionary. But if we were trying to learn a representation for all of the natural images, just pick a random image off of Google Images, maybe you would want an over-complete representation. In any case, here I just have a single image, so I'm going to learn an orthobasis. Okay, so y is q times x. Q is an orthogonal matrix. We want to make x sparse. And what I'm going to do, again, following very, very standard practice in machine learning and in applied areas of signal processing, is I'm going to try to do this by solving a big optimization problem. Really nothing special about this optimization. In fact, talking with some of Meet's students yesterday, we had pretty much the same thing up on the board. Right? I'm going to balance between my representation error, how well I'm approximating my input signal y, and the sparsity of my representation. So I write down an objective function that measures these two things, and then I'm going to try to optimize it over both the dictionary q, which is living on the orthogonal group, and the coefficients x. So, big optimization problem. Whether you believe you can solve this or not depends largely on your views on high-dimensional nonconvex optimization. This is a nonconvex problem. The constraint set, the orthogonal group, is certainly nonconvex. Also, in the loss here, in y minus qx, you have this bilinear interaction where you're multiplying q times x. So it's definitely not a convex function. Also, if I just think about the problem a little bit, my quality of approximation and my sparsity don't depend in any intrinsic way on how I order the atoms in my dictionary. So if I were to reorder the atoms in my dictionary, correspondingly reorder the rows of my coefficient matrix X, I would get an equally good representation from the perspective of this objective. So what it says is if I have one good one, then I have combinatorially many good ones, corresponding to all ways of reordering and maybe rescaling the columns of the dictionary. So it's not a convex problem, and it certainly doesn't have a single global minimum. In fact, any global minimum is going to give you combinatorially many. So potentially a hard problem to solve if you're really looking for the global optimum. So what I'm going to do is a very naive, fairly simple thing, which is to say, I don't know how to optimize this function globally. So why don't I just pick some starting point? I'll pick a random q to start out with, a random element of the orthogonal group, and then I'll just bounce back and forth. And as it turns out, this thing is easy to optimize if I fix q. Optimizing over x turns out to be a soft thresholding step. It's also easy to optimize if I fix x. Optimizing over q turns out to correspond to a singular value decomposition. You can solve it in closed form. So individual steps are easy. I'm just going to pick a random q to start out from, bounce back and forth until I think I've stopped. So what I'm going to show you is what happens if I do that many times, starting from many different random initializations q0. Okay, so I pick my q0 at random, and what I'll show you is the final objective function that I get after I've convinced myself that this thing has stopped. Okay, so here along the x-axis, you can see the different trials, right? So this is about 100 different trials. On the y-axis is the final value of the objective function, rescaled a little bit. So what you can see is, at least with respect to this random initialization, every time I pick a new initializer, I get a solution of essentially the same quality. And you can zoom in a little bit. You'll see differences at about numerical precision, but not much more than that. So the objective really is quite flat. So what it's suggesting is that at very least, there's some structure in this problem that lets me get solutions of equivalent quality. Right? At very least, it seems that the quality of what I get out doesn't depend on where I start. And you might hope that this actually corresponds to finding a global optimum. Right? If it were possible to find global optima here, this is what it would look like. Now you could ask, is this just specific to the fish? Is this something that happens in more generality? So here's another image. You can see the same thing. Do it again. We've tried it for thousands of images. We see pretty much always the same behavior. So it really seems like there's some kind of structure in this problem that's letting us find good solutions even though the problem is nonconvex. And so the question is, well, what's going on here? This is my own view on optimization problems until about 2 years ago. So there are the problems that I think I can solve. These are things that look like convex problems, right? Curving upward. Maybe has a little bit of auxiliary structure that lets me compute at least first derivatives. So these are the easy problems. And then I have the hard problems, which is everything else, which kind of looks like that. And so, of course, if I don't want to be over here, because then the quality of what I get out is going to depend a lot on where I start. And for signal processing, this really matters, because for signal processing, we'll see this when we get to the applications. Often we're solving problems where we don't just care about finding a good solution, we care about finding a correct solution. Right? We really want to be able to get down to the bottom, assuming that the bottom corresponds to the thing that we were actually trying to recover, or sense, or denoise. So the question is, what's happening in this problem that we've seen that's allowing us to somehow get down here, even though ostensibly the function looks like this. Now I'll say, in signal processing and machine learning and related areas, there's sort of tried and true methodologies for trying to handle problems that look like this. Right? The natural thing is you look for a convex function that approximates it somehow, maybe by taking a convex envelope over some set. You minimize the surrogate, and then you try to prove that you haven't lost anything in going from the thing that you wanted to optimize to the thing that you can optimize. So this has been spectacularly successful in some domains. Good examples are L1 and nuclear norm for compressed sensing style problems. This is beautiful when it works, right? It allows us to separate the formulation of the problem from the algorithm to solve it. You can prove things. You can get effective algorithms. It's great. The problem is that there are a lot of problems where this recipe doesn't really work out. Either we don't know a good convex surrogate, or the convex surrogate that we would like to write down actually is still not tractable. This is the case in low-rank tensor recovery, invariance of the low-rank approximation problem. Or we have a convex relaxation, but the convex relaxation just doesn't work that well. It's subject to some kind of limitation. And this is the case in a family of problems, which includes dictionary learning. These are problems where you're trying to estimate objects with multiple types of structure at the same time. So we'll talk a little bit more about how this shows up in dictionary learning. But in any case, the point is that while convex relaxation is very beautiful, there are a lot of times where, for whatever reason, I'm stuck with something that's non-convex. And, so then there's a different recipe there, which is what we just did, which is to pick a good starting point, let the algorithm loose, and hope for the best. And the kind of interesting observation is that sometimes this works a lot better than you really feel you have right to believe. And so our working hypothesis here is that actually, at least in the context of signal processing, there are certain families of problems where, although the problem is non-convex, when I've seen enough data, and the data are in some sense generic, the problem becomes easy to solve. And so, this is kind of a big and vague statement. We're going to make this precise in the context of dictionary learning and in the context of a couple of related problems. Now, the results that I'm going to show you about are not completely isolated. If you're working in signal processing or related areas, there's a lot of work that's been done recently on non-convex methods for recovering various types of structure, for matrix recovery problem, tensors, et cetera, et cetera. Most of this work has the following flavor. So what you say is, I have this non-convex problem, right? Maybe the function looks like that, maybe like something else. I'm going to think really carefully, and I'm going to try to cook up a good initializer, usually using a spectral method. So, if you do an STP relaxation to get close, solve an eigenvector problem. And then, if I'm close enough, what I can do is I can locally treat this like a convex function. Or maybe it's not convex, but at least it has some favorable geometry, such that I can prove that if I start there, I get down there. So, that's great. You can prove a lot of very beautiful results, very strong results for various problems in this way. Still, it's a little bit different from what we saw, right? In the experiment, we didn't do anything intelligent at all. We just throw the algorithm at the problem, and it seems to work. So it seems like, at least in this dictionary learning problem, there might be some global structure to the problem that lets us solve it without any need for special initialization. Okay. So we're going to talk a little bit about how this occurs. In particular, we're going to talk about how some of the ideas that I've shown you up to this point can be used to give provable algorithms for dictionary learning, and to give algorithms that work in regimes that we couldn't really address with previous methods, at least in terms of theory. So we'll talk about dictionary learning with fairly dense coefficient matrices. We'll talk a little bit about how this arises, and then we'll see some generalizations of this. And I should say, this is joint work with two extremely intrepid students, Qing Xu and Ju Sun from Columbia. These guys did an incredible amount of heavy lifting to make all the results that we'll see. Yeah. Yeah, no, feel free. It's a small
I spent wondering, the formulation that you're suggesting, which is kind of seems to resemble a lasso formulation.
It does.
Which is really subject to, implicitly, if we would provide certain priors, it's corresponding to a maximum fortiori over the signal. And in your case, not a signal, but a dictionary. I'm wondering myself, what would be the rationale for maximum posteriori? Because it doesn't really minimize anything. So what we're probably interested in minimizing is what's the expected error of our approach. And so maximum posteriori is just like a heuristic in terms of getting to the error. So do you have any rationale for that?
So what do you mean by minimizing the error? Can you help me out a little bit?
If you would have, for example, if you would have a model for the dictionary and a model for the coefficients and a model for the noise, then of course, well, not noise, error, then you would want to minimize the expected error. And I mean, the maximum posteriori, I understand if in this community, like, minimization of error hasn't been considered, I understand that, but I was just like, I would assume that a better approach would be, look, these are models for the signal, well, for the coefficients for the dictionary and for the error, and I would like to minimize the expected error.
But here, it's actually, he's talking about a structural problem. He's not talking about anything random. There is no noise, no nothing. It's a structural problem that he's setting up.
Yeah, but the lasso is obtained. The lasso corresponds to assuming that the coefficients are Laplace.
Well, but here is where we can. So I appreciate that as a perspective, and it's definitely true that if you assume that the coefficients are Laplace, then you get the lasso, and so that's, no one can argue there. It's also true that there are a lot of distributions that you can put on the coefficients that are not Laplace, under which you can still prove performance guarantees for the lasso, right? Which say that the thing that you recover is not too far away from the truth. So at least, I come to these. So we're going to talk about theorems in the talk. We prove things, but I come to this from the perspective of an engineer. I actually started out as an engineer, and often in practice, in the problems that we're working on, what we find is that we don't really have strong probabilistic assumptions that we really know how to make on the coefficients, or on the other aspects of the problem, right? I don't necessarily know the distribution. If I did, of course, subject to computational constraints, it would be a great idea to use that information. But for a lot of the applications that we run into, it's pretty easy to pose these sort of broad structural models that come from something like the physics of the problem. It's much harder to say, the distribution of the coefficients is not Laplacian, but is something else. It's harder to precisely specify that. And to me, and maybe I'm being naive or being intellectually undisciplined when I say this, but to me, at least from an engineering perspective, I'm not too worried about that. And certainly from a theoretical perspective, there's at least some backing that one can give for that viewpoint, right? Because the theorems for lasso, the theorems for L1 recovery, don't really assume that the coefficients are Laplacian. In fact, they work better when the coefficients are not Laplacian. So.
Okay, we can take it offline. Okay.
Okay. Yeah. No, I'm happy. I mean, we can. Maybe this is a more interesting discussion for everyone than the rest of the slideshow. I'd be
I'm
happy.
still curious to see the rest of the talk.
Okay, excellent. Yeah. And what I showed earlier, like I said, is corresponding to pretty standard practice, at least in applied areas of signal processing and machine learning. Okay, so yeah, so this is dictionary learning. Again, very widely used in practice. Algorithmic roots date back at least to some of the seminal work in the neuroscience literature by Olshausen and Field, and then subsequently by others. Tremendous amount of algorithmic work, tremendous amount of applications. I'm dizzy from all the applications that I've seen in the past 2 days from Hamid's group. So you know, lots of work on practice. Not so much that's known about this thing in theory from an algorithmic perspective. So what people try to do to study these problems from a theoretical perspective is they assume a model on the data generation process. And this may have more or less correspondence to what I really believe about what's happening in the world, but you know, at least it gives me something to think about for understanding properties of algorithms. And so the kind of model that's popular is to assume that my data actually was generated as some q times some x, and to assume that that x is a sparse random matrix. So I assume that entries are non-zero individually with probability theta, and then that the non-zeros are all Gaussian. And so if I make that assumption, then I can start asking for given classes of algorithms whether the algorithm can actually recover the q and the x. Right? So what are the situations in which it's possible to solve the problem in a strong sense?
So
yeah.
I'm asking why this assumption, why this particular assumption, like, has anything to do with the natural image you showed us in your experiment?
No. So this assumption is okay. So it depends. This assumption is a very good one for the application that I'm going to show at the end of the talk, which is in electron microscopy. It's not a great assumption for natural images. So for natural images, if you look at a learned representation, usually you'll see some decay in the coefficient magnitudes. That's not really reflected here strongly. You know, here I have coefficients that are hard on or off, and then conditionally they're Gaussian. So yeah, depending on the application, this may be a better or worse model. Okay, but in any case, so if I want to talk about when an algorithm succeeds, there are, at least in this model, there are kind of two parameters of interest. One is the theta that gives me the probability of a coefficient being on. The other is the number of data points p, right, the amount of stuff that I've seen. So at least from an algorithmic perspective, the first works on efficient algorithms that solve these problems, at least in some restrictive instances, are listed up here. So there's a joint paper with Dan Spielman and Wen Wang. This is from 2012. This is restricted to this case that I showed you, with the fish, where my dictionary is a square and invertible matrix. So this does the square case, and it does it in the situation where the coefficient matrix is highly sparse. So when this theta is smaller than about 1 over the square root of the dimension n. So this is an algorithm which solves the problem with provable guarantees efficiently in the highly sparse case, and in the case of a complete dictionary. So there's related work by two groups of theoretical computer scientists who show that you can solve the problem in the overcomplete case, again in the highly sparse regime. So when this theta is about 1 over the square root of the dimension, then you can prove things. These are using very different ideas. There's a complementary body of work on algorithms that are not as efficient, but can work for much broader classes of instances. So in particular, there's been some beautiful work recently on applications of the sum of squares approach. So you sort of do multiple rounds of STP relaxation, and then you can get algorithms that are not really practical, but are theoretically interesting because they work when the coefficient matrix is quite dense.
What are the typical conditions or requirements for these algorithms? For example, Are there some assumptions on the structure of the various matrices involved or anything like that?
Okay, so the algorithms that I'm showing you up here don't have any strong assumption on the Q. Here, for this joint work with Spielman and Wang, this was, you assume that the Q is square. These other algorithms can deal with overcomplete dictionaries. They neither assume nor exploit structure on Q. So you would presume that if you knew something about Q, you would do better. That doesn't show up here. So the assumptions in all of this work are that Q is general, the coefficient matrix is sparse and random. In the efficient algorithms that are known up until recently, the sparse matrix needs to be highly sparse. So that's actually quite sparse. In some of the less efficient algorithms, the coefficient matrix can be denser.
I see. So these have the flavor of deterministic results in sparse signal recovery from about 10 years ago. In the sense that for every Q over random X, there will be success.
Yeah, although you have to be a little bit careful. So there are two flavors of condition that you could give. One is I roll the dice, get a random X, want it to work for all Q. Mm-hmm. Another is I fix one Q, roll the dice, and I prove that I recover that Q. Right. This is the second one. I would imagine that you could do the first at the cost of higher sample complexity, mm-hmm. But so the viewpoint here is that there's a single Q that you would like to recover, and so that's uniformization is not as important. Okay, so the question is, so we have efficient algorithms that work in the highly sparse regime. We have less efficient algorithms that work for denser coefficient matrices. So is this sparsity assumption really necessary to have an efficient algorithm? In other words, is this just the price that we pay for not knowing the dictionary ahead of time? And as was alluded to, if the dictionary is known, then using work from about 10 years ago in compressed sensing, you can show that you can recover the coefficient matrices with strong guarantees, even if the coefficient matrices are fairly dense. So the question is this 1 over square root of n scaling actually the price of not knowing the dictionary? And so what we're going to do in this work is we're going to show, sort of inspired by the experiment that I showed you earlier, that that's not the case. That actually we can have algorithms that work even when this theta parameter is O of 1. So when we can work up to about theta a third. So you can have a number of non-zero entries that's proportional to the dimensionality of the signal. And the way that we're going to do that is using nonconvex optimization. But to get there, we have to take a little bit of a detour. So we're going to do this in the case of a square and invertible dictionary. So we're going to assume that this Q is a square non-singular matrix. And we're going to show in this case how we can solve some of these denser instances. And so the observation, if Q is square and non-singular, is that because in that case the row space of Y is the same as the row space of the coefficient matrix, I can actually transform this problem of learning the dictionary and coefficients to a problem of finding the rows of the coefficient matrix. And under our model, those rows are going to be sparse vectors. So geometrically, the problem becomes I have a linear subspace, which I know. That's the row space of Y. And I'd like to find the rows of X, which are sparse directions within that linear subspace. And again, the reason that I can do that is if Q is square, then the row space of Y is the same as the row space of X. So it sort of allows us to change the geometry of the problem. Usually we think about the problem in terms of the columns of X. Here we're thinking about it in terms of the rows of X. I was told that would make it go away. Okay, so that's what we're going to do. So the geometric problem is I have a linear subspace, right? That subspace contains a sparse vector, actually contains n of them, corresponding to the n rows of X. And I'd like to find those sparse vectors. So there's a kind of natural, if you're an optimizer, there's a natural approach to this, which is to say, out of all of the non-trivial directions within the subspace, let me look for the direction that uses the fewest number of non-zero entries. So let me minimize the L0 norm of Q transpose Y, linear combination of the rows, subject to Q not being 0. And of course, that's certainly not a convex problem. It's not even a problem that's easy to locally optimize due to the discontinuous nature of the objective function, the fact that the constraint is not a closed set. So we're going to need to relax the problem somehow. So these past works that I alluded to that get results in the highly sparse regime work by reducing this problem, this geometric problem of finding a sparse vector in a linear subspace, to a sequence of linear programs. So the idea is, instead of minimizing L0, I'm going to minimize L1. Again, reasonably sensible thing to do. Maybe there are better things, but at least as a first cut, this is reasonable. The big question here is how I handle the constraint that my direction should not be the trivial one, right? Because if I set Q equals 0, then I get 0 in the objective. So what this past algorithm with Dan Spielman and Feng Wang does is it says I'm going to minimize Q transpose Y1 subject to a linear constraint. So subject to a constraint that Q lives on some affine hyperplane. And then I try to be clever about how I choose the constraint. And it turns out, if you choose the constraint in an appropriate manner, then by solving P of these programs, I can, under the model, provably recover all of the rows of X and hence solve the problem. And this is something that holds, again, when the problem is highly sparse. It provably fails when the problem is not highly sparse. So sort of, for theory, it's nice. You have an algorithm that works in some regime, and you can prove sharp thresholds about its behavior. But practically speaking, it's not the best thing, because you can prove that it breaks down. Now, I'll say, Hamid, since we were chatting a little bit about these methods yesterday, so the way that you get this result is by choosing R to come from the data samples themselves. Mm-hmm. So if you make that choice, then you can actually see this one as solving the optimization problem min norm of x1 such that x is in row of y, xi is equal to 1, and then you do that p times. Mm-hmm. So actually, with the choice of R that works, this problem becomes equivalent to that one, which I think is more or less what we were chatting about yesterday.
Right, but Q for us is not is not necessarily square.
Right, which is a distinction. Okay, but in any case, in the square case, this is something that works well when the problem is highly sparse, breaks down when the problem is not so sparse. Okay. So what we're going to do for this work, let's just get rid of that one.
I'm sorry. Why does it break down when you have?
Why does it break down? Well, okay. So if you think about what you're trying to do. So if you think about what you're...
If it's too long, just move on. We can talk about it.
No, okay. So more or less, you're minimizing a convex relaxation of the problem, right? The problem has symmetry in it because there are n good solutions that correspond to those n rows of the coefficient matrix. The action of the linear constraint is to break the symmetry, right? Get you to prefer one of them instead of another. As the problem becomes denser, those symmetric solutions force the objective to be flatter and make it harder to break the symmetry until when you hit this square root of n threshold, actually at that point, the fully dense solution starts to be better than the sparse solution in an L1 sense. And it's like a board of derivation to show this.
Okay.
But that's basically it. So all the difficulty in relaxing these problems comes from the symmetry. And you can try all kinds of things to try to break the symmetry, but again, what we found is that actually just solving a non-convex problem instead can actually allow you to do better. So rather than having this kind of arbitrary symmetry breaking mechanism, we just do a simpler thing, which is more or less to try to minimize an L1 norm. Now, instead of minimizing it over a hyperplane, we're actually going to minimize it over a high-dimensional sphere. Okay, so now I'm minimizing norm of Q transpose Y1, subject to L2 norm squared of Q is equal to 1. And this is a very natural idea. This is an idea that's more than 10 years old. This is an idea that I guess is now at least 15 years old. People have been doing this in source separation and in other areas. So we're not claiming a lot of novelty on the formulation. But I think actually the interesting thing is that we'll see that we can actually say something about what this thing does. So actually this will turn out to be a non-convex problem that I can solve. Okay. So this is what I'd like to do. Again, my geometric problem is finding sparse vectors in a known subspace, the row space of Y. I'm going to do that by optimizing an L1 norm over a high-dimensional sphere. It's not too difficult to argue that actually the global optimizers of this problem correspond to the directions that you want, which are the rows of X. So that's not too difficult to show. The question is whether we can find them with some efficient algorithm. Now, a detail. Morally, I'm going to minimize the L1 norm, but to analyze it, I need to use the tools of calculus. And so actually, what we're going to analyze is an optimization of a smoothed L1 norm that replaces the point with something that's infinitely differentiable. But you can just think of it as optimizing an L1 norm over a sphere. And so then the question is, well, okay, L1 norm is convex. Sphere is obviously non-convex. So why is it that we can solve the problem? So here's just a picture to start to convince you that it might be the case, that we might be able to succeed. In this picture, what I'm drawing for a three-dimensional example is the objective function f of q as a function of q. Now, if you'll recall, this objective function is measuring how well I'm doing at picking out the rows of x. Okay, so x has n rows. I should expect that each of those rows and its negative corresponds to a point that I would like. Right? Those are my 2n good points. Those are in red here on the sphere. Right? So those are in opposite directions. So here I have 3 of them. And what you can see, this is the objective function as a function of q from a very large number of samples. What you can see is that actually in this experiment, those points are the only local optima. Now, you'll notice there's some kind of interesting structure to the thing. You can see some saddle points there. You can see some local maxima. But the only local minima, if you look around, actually correspond to the points that you want. And so the way that we're going to do analysis here is we're going to prove that that's something that obtains in general. So another way of seeing this, or thinking about the structure in the problem, is to imagine that I'm putting a coordinate chart on the sphere. Okay, so I have the sphere. What I'm going to do is I'm going to take the northern hemisphere and I'm going to project it onto the equatorial plane. Okay, so I reparameterize the northern hemisphere. And now I draw the objective function as a function of the point on the equatorial plane. Okay, so again, there are 2n good solutions. Those are corresponding to the standard basis. And the North Pole. North Pole maps to the middle. And what you can see is that the objective function is kind of acting like you've taken a concave function. It's certainly not convex, but it's acting like you've taken a concave function and then you've symmetrized it around. Right? So it's like it's a piecewise concave function. And you can see that the way that it joins actually makes it such that even at the joins, there are no spurious local minima. There are saddle points there, but no minima. Okay, and so to prove things about the behavior of the algorithm, you need to show that this is something that obtains in general. So it's not that difficult to do this in a population sense. So you look at, if I think about this objective function, I can think about this as a random process, right? The randomness is coming from the randomness in the data generation process. I can show that the expectation of that objective function has the desired property. In particular, if I look at it in this coordinate chart, then there's a region around the target point, very small region where it's acting like a strongly convex function. Move away a little bit, there's a non-trivial gradient sloping up. And then if I go further, I may have some stationary points, but at each of those stationary points, I have a direction of negative curvature. And so I can prove that the expectation of the objective function is something which is amenable to optimization. Okay, so that's for the objective function, the expectation. That's something that obtains even when this theta is relatively large. So this theta was the probability that a given coefficient is non-zero. Before, it was forced to be smaller than 1 over the square root of n, again, because of this difficulty with symmetry. Here, theta can be as big as a half, and this property still obtains. Okay. And so then the question is, okay, if I don't see the population, I don't see the population version, but I see the finite sample version, how many samples do I need to see such that this happens for the finite sample version as well? So it's kind of an interesting probability question to think about, because what you'd really like to know is, if I let an algorithm loose on the finite sample version, how big does P need to be such that that algorithm does essentially the same thing as it would on the population version? So that's kind of an interesting question to think about. In this work, we're thinking about that in a kind of heavy-handed way, right? So, usually when we think about empirical processes, we think about how far away they are from their expectation. That's not really the right notion for algorithms, but you can kind of adapt it and say, well, if the gradients and Hessians of this finite sample version are uniformly close to the gradients and Hessians of the expectation, then from the perspective of the algorithm, the finite sample version is essentially equivalent to the expectation. So we can analyze the convergence of the gradients and the Hessians in L infinity, right? The worst deviation between this one and this one. And we can prove that when P is, well, at least large enough, so about n cubed, when P is about n cubed, then exactly the same behavior obtains for the finite sample version as for the population. And so in this result, again, the theta can be as big as a half, right? So we're certainly in the proportional sparsity regime. P needs to be at least n cubed. That seems to be intrinsic, at least to the algorithm. Also, there's some dependence on the amount of smoothing that we've done in the objective function. That seems to be an artifact of our ability to approximate hard integrals rather than anything that's real. But about theta about O of 1, P about n cubed. Okay, and so what it proves is, at least if you've seen enough data, then this objective function is very friendly for optimization. So even it's non-convex, it has properties that I can use to find correct solutions. Now there's a question of how I actually use those properties computationally. There are basically two issues to think about here. One is that I have an optimization that's not on a Euclidean space, right? It's on a Riemannian manifold, a high-dimensional sphere. The other is that although the problem doesn't have any spurious local minima, it has a tremendously large number of saddle points. And this is kind of a generic concern in representation learning. People see this in problems involving neural networks, that often local minima empirically are not that big of a concern, but there's always a need to escape saddle points. And you can kind of see this as a consequence of the symmetry in the problem, that you're going to end up with these saddle points. So in practice, very simple algorithms work well to make sure you don't get stuck. In practice, something like a randomly perturbed gradient algorithm will be fine. For a theory here, we're actually using a second-order method, which is a trust region method. And that trust region method is explicitly taking into account curvature information to make sure that I don't get stuck there. So that method is going to have the property that for this problem, no matter where I start, I get to the correct answer. Okay, so then there are details. So for those of you who haven't seen the trust region method, what the trust region method does is it says, I have a problem that I would like to solve. I have some function that I would like to optimize. I'm going to build a local quadratic approximation to the function, just use Taylor expansion. And then to get my next point, I'm going to optimize that quadratic approximation over a ball, over a neighborhood. And it turns out, although these problems are non-convex, so the second order term in the quadratic approximation might have some negative eigenvalues, even so, that problem of optimizing a quadratic over a ball is one that you can solve efficiently. So you do a sequence of these so-called trust region subproblems, each of which approximates the objective function, then optimizes the approximation over a ball, and this converges to a local minimum. So there are details in how you do this over a Riemannian manifold instead of doing this on Euclidean space. But those details, at least for our purposes, are mostly formal. The sphere is actually a very, very friendly Riemannian manifold. So you just make your approximation over the tangent space, and then you need to understand if I want to move in this direction, how do I map that back to the manifold? Here via the exponential map. But in any case, the geometry is very simple because it's just a sphere. So I guess the important generic concern is that in learning representations, for example, in learning dictionaries, we often run into problems with a lot of saddle points. Trust region method is a good way, at least for theory, to make sure that you don't get stuck in saddle points. And actually, numerically, there's a very beautiful package by these guys, Absol, Mahoney, and Spolker. It's just very, very well done that you can use. They have nice implementations of this. Okay, and so I can use the geometry of the objective function to prove convergence. That's something that we can do. We won't really dwell on it here. The intuition is simply that at every point that's not a target point, you either have a strong gradient or you have a strong direction of negative curvature that I can use to prove that the objective function decreases. And so you make constant progress in these regions, and then when you get close to the truth, you can show that it's quadratically convergent. Okay, so that's for convergence. And so the upshot of all of this is that for this problem that we started out with, this problem of learning a complete dictionary, we can have a method which is efficient, takes polynomial time, uses polynomially many samples, and it works even in the relatively dense regime. So even when this theta parameter, the probability of being non-zero, is a constant. So that's, at least for the algorithms that we've been talking about before, that's a regime that was pretty far out of reach using convex relaxations, using linear programming, using ideas like this. Okay, so that's a result. This is just showing this numerically. This is a thing that happens. Here's correct recovery. Here is failure. So it's kind of interesting that although the problem ostensibly looks a little bit challenging, it actually has this structure under the hood that lets you solve it. Still doesn't quite prove that we always get global optima for real data, right? That was the question that we started out with. We don't have any proof of that, but it really is at least suggestive that there's something interesting going on here. And it turns out this is a structure that obtains not just for this problem, but for a family of problems. So this happens in dictionary learning. It happens in a couple of other problems that are of interest for machine learning or for numerical linear algebra. A classical example is the eigenvalue-eigenvector decomposition problem. So again, this is a non-convex optimization problem over the sphere. You can prove with just about a page of derivation. Actually, this is a great exercise if you want to get familiar with the Riemannian geometry of the sphere. You can prove that the optimization problem of finding the eigenvector that corresponds to the maximal eigenvalue has this property that every local optimum is global, all of the saddle points have negative curve, have positive curvature, and so you can, conceptually at least, it wouldn't be a great algorithm, but conceptually at least, you can find global solutions. So this happens for eigenvalue-eigenvector decomposition. It happens for problems in tensor decomposition. These are problems that are of interest, for example, for method of moments in machine learning and in statistics. Another place where it happens that I'll just sort of briefly mention, since I'm nearing the end of my time, is in a problem that's known as phase retrieval. So this is work that was really pushed by my two students, Ju-Sun and Jing-Chu. They got excited about a talk that they had heard about this phase retrieval problem. They wanted to see, what was going on here. So this phase retrieval problem is one where I start out, my target of interest is a complex value vector. So this x0 is an n-dimensional complex vector. I see measurements of the magnitude of its Fourier transform, and then my goal is to reconstruct that complex vector x. And so this is something that shows up in audio applications, it shows up in imaging applications, it shows up in a lot of different places. It's a very classical problem. There are classical algorithms. Recently, this has seen a lot of development and a lot of interest from this sort of compressed sensing perspective, where people try to prove various guarantees for the performance of algorithms. In particular, there's been a lot of work on this abstraction of the problem, where instead of recovering x0 from the magnitude of its Fourier transform, I recover it from the magnitude of some kind of linear measurements, where this A is some matrix that I might have some freedom to choose. And in particular, for this problem, people look at this kind of natural non-convex formulation. This one was analyzed in Kendez, Lee, and Sultan-al-Khattabi. What this is doing is it just says, okay, I have my M measurements. These are moduli of rows of A on x0. Right? So it's a magnitude of an inner product. Let me find an x that gets me as close as possible in this sum of squares sense to my measurements. Right? So I just minimize this kind of goodness of fit. So kind of natural problem. You can prove, if you do spectral initialization here, so you sort of solve an eigenvector-eigenvalue problem, you can prove that from about n log n measurements, where n is the dimension of the vector, one can find the true vector x0 up to a very small error. That's work by Kendez, Lee, and Sultan-al-Khattabi. What my students Zhu and Qing were able to do was to show that actually this problem has a very similar property. Namely that if I've seen enough measurements, here this x was of dimension n, so if I've seen about n log n, here log cube, that's sort of a concession to the limitations of our ability to do analysis, but about n log n measurements, then actually this problem also has the property that every local minimum is global, and no matter where I start, I get the correct result. So kind of similar to what I saw before, I have the target points. These are sort of phase-ambiguous versions of the original vector. I have some local maxima. I have potentially a very large number of saddle points, and that's it. And these saddle points are structured such that they're easy to escape. So, again, no matter where you start, you get the correct answer. And that's something here that happens with just about the minimal number of samples, up to about a log cubed factor. So again, just suggesting, even though there's nothing really all that unified between how we prove this and how we prove the previous result, suggesting that in a lot of these kind of natural non-convex problems that one might choose to solve, there might be some interesting underlying geometry that actually lets you get correct answers. So there's potentially a reason why these things work so well. Okay, so I guess I only have about 5 more minutes?
5 minutes.
5 minutes at most. Okay, so I'll talk a little bit about some applications that we've been doing of some of these ideas. This is an application in electron microscopy. This is Abhay Pasupathy. He's a physicist from Columbia. He knocked on my door with the following problem. So he works on electron microscopy. This is a scanning tunneling electron microscope. So you have a material that you want to understand. You put this conductive tip that's at atomic scale, very close to the material. And the idea is, by quantum mechanics, there's some probability that I just, there's some very, very small probability that I just jump back to New York in the next second. Avoid the need to deal with United Airlines. If I'm very close to New York, then there's a much larger probability of the jump happening. And so if I put this thing close enough, there actually is a current that I can measure, which is going to tell me things about the property of the materials. So here, this is an example of what you see. So I have two spatial dimensions. These are corresponding to different locations of the tip. The last dimension is energy. That's actually corresponding to the applied voltage between the tip and the surface. So I get this high-dimensional observation, which is a kind of cube. It has dimensions of space cross energy. And this becomes interesting for things like understanding the properties of novel materials, conductivity, flexibility, things like this. It especially becomes interesting because for a lot of these materials that people are looking at, the structure is far too complicated to work out the behavior of the material from first principles using quantum mechanics. So you kind of have to do something experimental, figure out what's going on. And it turns out a lot of the structure is actually dictated by these kind of characteristic patterns. That they're called defects, but actually are kind of the thing that you want in the material, that actually happen at different locations in different points in space, where you have some sort of deviation from the underlying crystal lattice. And so that shows up here in space cross energy as these characteristic, if you look around, they're kind of repeated patterns in your observation. All right, so the goal is to find these things. And so, of course, in this situation, I just ask my student to look at this and draw a box around it. But for the materials that people like my collaborator or I really care about, it's not that easy. Things get a little bit denser, and it's harder to tell what's going on by eye. So what people classically do in this area is they take each slice of this thing, each energy, and they take the Fourier transform. Okay, and then from the Fourier transform, here's the thing, here's its Fourier transform. They look at the magnitude, and they try to eyeball it and sort of get some hypotheses about what's happening in the physics. So, if the problem is very, very sparse, if you just had one defect, then that's great. You can understand very clearly what's going on here. You see this kind of very beautiful pattern in the Fourier transform that's telling you things about the state of the phase of matter of the material. It's telling you a lot of things that you would like to know. As you add more and more of the defects, there gets to be this kind of problem of phase, where instead of just seeing the Fourier transform of this one, I see it superposed with the Fourier transform of translated versions of it. And so I lose a lot of the detail, and by the time I get back to the real data, I've lost pretty much all of the detail. So, if I knocked on my door and said, how can we deal with this? So to me, this looks kind of like a deconvolution problem, right? I have this defect signature that's happening at characteristic locations in space. It's actually multidimensional, right? It has as many dimensions as you have different energy levels. And what I see in my different slices of the observation are the convolution of this one with this activation map. So, you can see this as a kind of dictionary learning problem, where I'm trying to learn both the defect signature and the activation map. Although here, the way that the dictionary interacts with the activation map is slightly different. It's still a bilinear operator, but now it's by convolution instead of by matrix multiplication. Okay, and so the question is, if I see Y, how well can I do at figuring out A and X? Okay, and so again, there's a kind of natural nonconvex formulation. This also was up on the board in our discussion yesterday. I have minimized some combination of data fidelity and sparsity. For theoretical purposes, it's often useful to think about this thing as optimizing a kind of, I'll call it marginalized objective. It's not really marginalized, but optimize an objective which depends on A only, where I've optimized out over X. The reason for that is that it's a pretty good model to assume that the sample is big here and the defect is small. And so when that happens, then I get a kind of similar concentration of measure phenomenon where this objective over the defect signature only starts to look like a kind of large sample limit. Although proving that, analyzing that is a little bit trickier. Okay, but in any case, you again get an optimization problem over the sphere. This one does not have the property that every local minimum is global, but it does have some other pretty good properties that you can use to solve the problem in reasonably general circumstances. In particular, there are some situations where you can show that every spurious local optimum corresponds to taking the true defect signature, shifting it, and then chopping it off, so making a shift truncation of the truth. And so that's actually, if you sort of use that as an inner tool in a larger algorithm, you can use that observation to do pretty well, both in simulation and on the real data. So this is an example. Here's the data. Algorithm correctly picks out where these defects are, correctly picks out the little signature. And this is just a comparison. This is, not doing anything really fancy in terms of optimization or in terms of analysis, nothing all that fancy from our perspective, just kind of the natural things. But from our collaborators' perspective, this is very nice because this is the thing that they would have gotten before, just doing the FFT. This is the thing that you can get now. And again, we're trying to do some analysis here, prove some things. We can do it in certain cases. We can't do it in other cases. But yeah, this has been a lot of fun. It's one of these domains, number one, where you care about having correct results, right? You really want to know what's going on in the material. Number two, there's a lot of room for good tools from modern optimization, signal processing to be helpful here. Okay, so I think in the interest of time, I won't talk about some of the computer vision applications. Those are a lot of fun too. You can try to do all kinds of things in terms of building representations that both have good physical properties, do a good job of sort of uniformly approximating an object of interest, and also have good computational properties. They sort of correspond to linear maps that you can evaluate efficiently. That maybe is a little bit much for the time. So I'll just conclude. So the main problem that we studied in this talk was this problem of learning sparse dictionaries from observed data. We showed how we could give an algorithm for that problem, which works even in this so-called proportional sparsity regime, so even when the representation is not all that sparse. This is better than our own previous work on the problem, also than what was able to be achieved with other algorithms, in the sense that this works with much denser coefficient matrices. So previously there was this 1/√n barrier. Now we can get up to O of 1. There are caveats. I only know how to get this kind of result for complete dictionaries. The dictionary needs to be square. Also, if you look at the theory, you can extract a result on stability under noise, but I haven't tried to optimize this in any way. So it's much more of a recovery than an estimation result. There are a lot of open questions here. You can think about all kinds of other non-convex problems that you might hope have similar structure. You might like to be able to prove things about them. Also from the algorithmic perspective, since we know a little bit about the geometry, then it becomes interesting to ask whether we can have dedicated algorithms for that purpose. Okay, and so with that, I'll just thank again my collaborators. The papers are pretty much all online, and thank Hamid for the kind invitation, all of you for your attention. Welcome any additional questions or criticisms.
Now you let it rip.
So just in general, you work in a complete sense where you also have orthogonality.
Yeah, so this is a point.
At the beginning.
This is a point, right? So this is a point that I sort of skimmed over quickly in the interest of time. We also have a result for dictionaries that are not orthogonal, but you pay a little bit in the sample complexity. Basically, you pay in the sample complexity in terms of the condition number of the matrix that you're trying to recover.
Okay.
So, you know, from a theoretical sense, it's better for orthobases.
So what I was wondering is that some of the questions that were asked, it made me think that maybe, have you ever looked at your formulation? It seems like there's no reason that you couldn't put in the analysis dictionary sense rather than the synthesis dictionary sense, and it would provide a different insight.
Right, and that's something that Hamid mentioned as well, because, you know, I mentioned this linear programming algorithm. His former student, who I guess you know better than I do, has a you know, completely independent generalization of this to analysis dictionary learning. We've been thinking mostly about synthesis dictionary learning, but I agree, at least in the orthobasis case, they're, you know, immediately convertible. You could think about that problem.
Well, I was
as well.
thinking like your normal distribution, your Bernoulli distribution, or whatever. Like you could potentially get different insights by considering different applications in that sense.
Right. Although to be honest, I would like to, because I think the theoretical results become more powerful if you can minimize the strength of their assumptions. Of course, I'd like to be able to de-randomize the result, get rid of that model of the coefficients. I think it's possible, but I only really know how to do it under conditions that make the coefficient matrix very close to a Bernoulli Gaussian matrix. You basically ask the sparsity pattern to be an expander, and then some diversity in the signs, and you can make progress.
Actually, for instance, in wavelet analysis, you know, the Bernoulli Gaussian, in other words, now you actually model the coefficients as Gaussian entities,
right,
with the location as a Bernoulli, on and off type of thing.
Right.
Actually, we proposed this model in mid-90s or something like that.
Sure.
And it actually, and then you apply that in a Bayesian setting. It actually works quite well. For searching for like wavelet packets and things like that. It actually works quite well.
Okay, so maybe I don't have to disclaim as much about to me.
It's amazing. I mean, it's a simple idea, right?
Yeah.
But yet it's pretty powerful.
Yeah, I mean, to me that's necessary because I don't know how to do theory without it. What I'd really like to do is I'd really like to identify some deterministic conditions that explain what we saw at the start of the talk. Because the idea that these algorithms work really is not a theoretical figment, right? You throw it with the real data, and you can see it's doing the right thing. But to make progress on this problem, at least with what we know, we need some assumptions, and that seems to be one of them. But if it's justifiable, that's great. And I will say, for the physics problem that I showed you, that it's actually a very good assumption. Actually, you would do a little bit better probably to say that the locations come from a Poisson process, but the Bernoulli model is not too bad. For natural images, I'm not as sure.
Any questions? Any other questions? I do have a question. This phase retrieval problem sort of is intriguing to me, to say the least. Now, you talked about, I wasn't familiar with this quote-unquote generalization where you have a matrix. Basically, the magnitude of your signal multiplied by a matrix. So what do people? I mean, what do you do there exactly? I missed something.
Okay, so people in that sort of compressed sensing community have gotten.
I know Condes is. That's all he talks about these days.
Yeah. That's actually where this came from. I was not. My student, he came and gave a colloquium, and my students got really excited about it.
Yeah.
Wanted to do something. So there. So the natural problem to look at is recovery from the magnitude of the Fourier transform. That's something that happens in a lot of different settings for physical reasons.
Right.
Unfortunately, that problem is somewhat ill-posed there are some situations, so if you oversample a little bit, then you can at least have a uniqueness result. But in terms of having the structure that you need to get a guaranteed algorithm, it's kind of hard. Although I'm trying to convince Ju to look at that a little bit. I'm hopeful. We'll see. So this generalization of the problem, you assume that you're seeing not the magnitude of the Fourier transform, but the magnitude of some general linear map. Mm-hmm. And so so there are a couple of classes of linear maps that you can look at. For example, when people try to build systems that implement these results, then this corresponds to making different masks when you take your measurements. If you're doing diffraction imaging, then you put a random mask on, and so that sort of mask is playing the role of your measurement operator.
Right.
People also look at recovery instead of from the Fourier transform, which is ill-posed. They look at recovery from the short time Fourier transform. So that's another example of an A that you could stick in there. That also turns out to be a little bit better than the Fourier transform. And so, once you've made this assumption, assuming you've made peace with the presence of that measurement operator there, and you believe that map solves your problem, then you have sort of either an algorithmic or statistical problem to study. People study convex relaxations of that based on semi-definite programming. They also study non-convex methods, which tend to be more efficient. And so what Ju and Qing were able to show is that actually for the natural non-convex method, it has this property that allows you to globally find solutions. Now, that non-convex method had already been analyzed by Candez, Lee, and Sultano-Khattabi. What they showed is that if you have a good initialization, and they showed that if you have a good initialization, if you have a good initialization, then you can get the correct answer there. And so what Ju and Qing showed for that problem is that actually you don't really need the initialization. There's just this global structure to the function that lets you find the right answer.
Interesting.
But yeah, we're thinking about this phase retrieval actually in the context of some of the microscopy applications. Because if you think about how that observation looks, you have your characteristic kernel. You can view the locations of the kernel as random, and there are a lot of them in the sample, right? So if you just sit down and think about it a little bit, it's not too hard to, based on that, to derive a consistent estimator for the autocorrelation of the kernel, just using the fact that it's short, and then you see it superposed with itself in random ways. And so if you have the autocorrelation, then you actually have the magnitude of the Fourier transform. Mm-hmm. So if I wanted to, if I could solve the phase retrieval from magnitude of Fourier transform, then I don't even have to do non-convex optimization. I don't even have to do deconvolution. I just do that. So that's a thing that we're thinking about, or at least how to use that information in that application.
Interesting. Any other questions? All right. If not, let's thank our speaker again.